Hi everyone, welcome back to Cody's Lab. So today I want to try making a model of a confined aquifer. So what we've got here is the basin, which is going to be holding the water. And actually for the well, I'm going to be using bubbler stone connected to this clear tubing here. So you've basically got the hole in the ground, which is the well, and then down near the bottom where the aquifer is, you got the filter pack. This is to keep the sand from going into the hole. Real life wells have that. Now I've got some water that's dyed blue so to make it easier to see. I've got some clay, and down by my feet are some buckets full of sand. So the sand is going to be our water storage medium in the actual aquifer. So let's start putting in the sand here. So think of this like a river is currently depositing sand here, or gravel, or something that is good at transferring water. There's our transmissive layer of sand, which can hold water. Now of course this probably in real life would be already full of water, so let's start adding the water here. And now what we've got is an unconfined aquifer. Basically the water is only pressurized to atmospheric pressure and its own head height. So with this type of aquifer, all we have to do is dig a hole, and the hole will fill up with water as the water comes in from the sand. Maybe you've got your river channel. The water flows into the river channel because it's a lower spot. If I dig this sand away, you should be able to see that the water level inside of our well bore here is about the same as the water level of the aquifer. See, if I pull water away, you can see it'll begin to drop and then the water comes back up. It's a little bit higher, and that's due to capillary action, which you wouldn't really see if you had a large well, because capillary action increases the smaller the hole. Yeah, you can see it's matching right up with the level of water. Alright, so let's push the sand back up against this, level this all out, and now we need to add a layer of something that slows down the flow of water. An aquitard, if I'm remembering my terminology correctly. Now clay is the obvious answer for what this aquitard will be made out of, because clay absorbs water and it makes it very difficult for the water to go through it. It forms an almost impenetrable layer. Now how you would get this is, say the river meandered away and then you start depositing smaller material, or perhaps a lake formed and you get some sediment at the bottom of the lake. But ultimately this forms a cap that the water has difficulty moving through. This will confine that lower aquifer there. Hence the name of confined aquifer. Okay, now that I've got my clay layer in, I'm going to have to let this absorb water, which is going to be slow because water moves through clay slowly. I might even have to spritz in some from the top here. I'll give it an hour or two to get fully moistened. So there's the clay in, and it's thoroughly hydrated. I actually ended up adding a layer of bentonite, you can see here, just to make sure it seals very well. And you can already see a little something here. See that? The water level has been pushed up above the layer of clay. That's because the weight of the clay is now pushing down, and since it's heavier than water would be, it's creating more pressure. So now the pressure in this aquifer is now high enough to actually force the water all the way out to the ground surface, but the clay is holding it down. So the water can't just go right up through the clay. Let's turn this up to 11 and add another aquifer on top up here. Let's use a different colored sand, shall we? I almost forgot. But let's add a second well in here into the unconfined aquifer that we're making. This way we can compare the water height. Oh no, we got some water escaping. Look at that, the water has found its way up through the clay. That's annoying. It's going to ruin my test. Is there a way I can plug this? Yeah, but is there going to be others like that? Probably. So I've just filled all the empty spaces in the sand with water. In fact, I've now got standing water up here at the top, so I guess this would be, let's call this a river channel right here, a really wide river or something. So the unconfined aquifer is just about even with the water table, and the confined aquifer has got the water pushed all the way up here. In fact, I bet if I were to turn this over, I could siphon water out of it. Essentially what I've got here is an artesian spring, or an artesian well. See? The water is naturally coming up out of the ground under pressure. And I'll be able to get a little bit of water down here. You might be asking, where's this water coming from? You see, water can't flow down, like it can't go from here past the clay layer and into here. In fact, the water is coming from what was trapped in here. The sand is compacting under the load, but the water is actually forming just a little bit of a back pressure, keeping the sand from compacting. But as the water leaves, the sand can compact. And so the actual entire ground surface is dropping slightly as the water is being pumped out, or pumping itself out by the weight of the ground above it. It's able to do this because the sand has a higher density than water, and it's got water in it, but the sand itself is so heavy, it's able to overcome the hydraulic gradient and force the water higher than you would normally expect. And that's actually pumping out quite a lot of water. It makes sense. You can store a lot of water this way, but these are very difficult to put water back. These confined aquifers do recharge, but very slowly, and usually not straight down, but rather water that's coming out from maybe some mountains. It just goes really deep and then tries to come back up. Once this ground is compacted, it's not going to just spring back naturally. You'd have to really force the water down there to get it to spring back. Once this is compacted, it's lost your storativity forever. There's a little bit of storage you can get at that point due to the compressibility of water itself, but it's not very much. In fact, I think this is just about done. Yeah. So it's compacted. You could add more weight here, and I could force more water out by compacting the sand tighter, but... So I'm going to take my hand and I'm going to force down on the sand here. So I'm going to push with a lot of pressure. I'm going to watch down here. I've trapped a bubble in the line, and if the water moves, if I'm able to get more water to flow, that little bubble should pop out. So here it goes. I'm going to push on the sand, increase the pressure, and it'll pop out. Well, I guess there is a little bubble there, isn't there? Increasing the pressure does cause the more water to force out, so this sand isn't fully compacted just yet. That's not really a practical thing to do. Now for this unconfined aquifer, I actually have to do work to pump the water out. You might notice that the water here is a different color because I didn't add the dye to it. And also it's a lot more murky. It's not a good water quality, but that's mostly just because of the type of sand I've got it with. Watch what happens when I've got some wells spaced out away from the pumping well. Maybe call these ponds. But let's just start pumping. I'm just going to suck the water out with my mouth. See, the first one has already been emptied because it's right next to the well. See that? What we've caused is a Kona depression. This whole area here is now without water. The water's got to flow in from elsewhere, and there might actually not be enough water to do that, so let's just add the water back a little bit here. We should start seeing the water come back. Yeah, so this case it came kind of off to the side here. You can see that? That's because the water has trouble flowing through the sand. It actually creates a resistance that slows the water's flow down. So the closer it is, the faster it moves towards the source. And also the area, like the distance the amount of water within a certain distance is also increased the greater the distance is, the area of a circle or whatnot. And that's how these confined aquifers can actually hold on to water even if the clay layer above them doesn't completely cap it off. That's because the water here has to move through the material to find a way out. That's why I had a little bit of time to work to actually pump a little bit of water out of it, because the water couldn't just flow out instantaneously. A confined aquifer would also form a sort of cone of depression, but the water can't really actually move, so it's not actually the water's level, but rather the potential head, the potentiometric surface that gets drawn into a cone. So basically you have lower pressure near the well and higher pressure elsewhere. I'm going to try this again. That is kind of fun watching the cone of depression expand out. Here, let's not pull out as much water out. So now we should be able to see them recover. Let's stop the pumping here. And there we go. Alright. This was a lot of fun for me. I'm not sure if I conveyed the information nearly as well as my geology teacher, but hope you enjoyed at least. I'll see you next time.